Good morning, Dhar sir.
Sir, yes, sir.
Good morning, Dhar sir.
Good morning. Good morning.
Good morning, Dhar sir.
Good morning, Das sir.
So, welcome again. And what we will do, we will start the first session of the FDP on multivariate data analysis for engineering, science, and management. For this session, the speaker will be Professor Joydeep Dhar. Professor Joydeep Dhar is a professor in Department of Mathematics, ABB IIITM Gwalior. He has done his PhD from IIT Kanpur in 1997, and he has more than 20 years experience in teaching. His areas of interest are industrial mathematics, mathematical modeling and simulation, EWS management systems, financial mathematics, fuzzy logic applications, and statistical learning. So today he will take this session and he will be delivering a talk on basics of multivariate data analysis. So over to you, Dharshak.
Okay. Thank you, Ajay sir. How many participants are there? There are 30 around. So all the participants have joined.
Sir, there are 200 participants, but at present there are 32.
Okay. Okay, I can start my.
Please start, sir.
Okay. PPT is visible?
Yes, sir, it is visible, sir.
Not now, sir.
Sir, you have stopped sharing now. It is visible now, sir.
Now it is visible?
Yes, it is visible, sir.
Yes, sir. Yes, sir.
Okay. As Professor Ajay Kumar has actually introduced that this FDP is on multivariate data analytics. So for multivariate data analysis, the fundamentals or the basic concepts of statistics, probability and stats are required. So the first two sessions that I will take on, this is basic concepts on probability stats, and especially on different types of distributions like discrete, continuous distribution. It is a single variate or multivariate. So the first session I will actually start with very basic probability concepts, and then we'll discuss few discrete and continuous distribution. And in the second session, as actually in that schedule already mentioned, that second session will be multivariate discrete and continuous distribution along with the matrix algebra. So in the second session, I will start with matrix algebra first, and then we'll discuss this multivariate discrete and continuous distribution. So I know that all of you know about the probability and stats of the fundamental basics of the definitions of probability, and this is simple statistics are all of know, but still I will take a few slides quickly. I will actually brush up or probability and stats fundamental or the basic concepts, and then I will jump to the discrete and continuous distribution. So I start with this is introduction of this. Say why learn probability. So this is nothing in life is certain. All of you know that uncertainty is everywhere around us. Even in the, we know that in the COVID situation also, we know that we don't know that this will be safe for a certain period with this COVID infection or not. So it is actually, uncertainty is from business to medicine to the weather, everywhere. The probability provides a this quantitative description of the chances or the likelihood associated with the various outcome. It provides a bridge between the descriptive and statistics. It means that populations and samples are there. So we can have probability and statistics, and that after taking a sample population, we can apply, we can calculate that what is the likelihood chances. So that particular thing will happen or particular event will happen. So, and interferential statistics can give you that what will be the, if it is actually, we don't know exact event. So, but from there, we want to, this is inferences. So inferences we can do through statistics. So like probability versus statistics, that we can, very simple example, you will understand that what is the probabilistic logic and what is the statistical logic. So probably, suppose I know exactly the portion of car makes in India, means we know that there are different car makers in India like Maruti Suzuki, there are Ford, there are other there are Honda and other. So then I can find the probability that a first car I see in the street is a Ford. This is probabilistic reasoning, as I know the population because I know that how much car produced by means how much fraction of the car produced by Maruti Suzuki, how much by Ford, and so on. So this logic or the this reasoning is actually called probabilistic reasoning, because I know the population and predict the sample. Now, if I see in other way, that now suppose that I do not know the portions of the car makers in India, but would like to estimate them. I observe a random sample of car in the street, and then I have an estimate of the portion of the portion of the population, and this is statistical reasoning. Means in the case of probabilistic reasoning, you can see that I know the population is known to us, but here in the case of statistical reasoning, we don't know the population. So this is about the population means population, that how much portion, that this example, that how much portion of the different car maker makes the car means car available in India. So but we can take a sample of car in the street, and then I have an estimate of the portion of the population. This is a statistical reasoning. So you can understand what is the thin line between the probabilistic reasoning and the statistical reasoning. So now I start with very basic concepts, that an experiments is a process by which an observation is obtained. An event is an outcome of an experiment, eventually denoted by a capital letter. Event A, B, C, D, whatever the capital letter in the statistics, we use the capital letter for events, and the basic elements in which probability is applied. And when the experiment is performed, a particular event either happen or it does not happen. Say in the case of tossing of coin, I'm looking for head is our event. So we can get the head, or we can get the tail, means not head. So this is actually the experiment, that particular event either happens or it does not. So experiments and events, say just an example, that experiment like record an age. I'm recording the age of different people. Say A is a person is of 30 years old, and B is a person older than 65. So it is greater than 65, the age of B. So like another, the tossing a die. So in that case, that A is observed an odd number and B observed a number greater than 2. So so now these are the like an this is experiments and events. Events is the actually I'm just supposing that event is our say we are looking for, in the case of dice, we are looking for that it is odd faces coming out or not. So in that case, we are tossing the die, and then we can observe that it is happening or not happening. Basic concepts, are extending the basic concepts. The two events are mutually exclusive if when one event occurs and other cannot, then or vice versa, then we'll call it as a mutually exclusive, means both the event simultaneously never possible. Like tossing of coin, so either it will come head, if a fair tossing of coin, so either it will come this is head or tail. So it is, if one comes, then other can't. So experiment of tossing a die. So observed an odd number, observed a number greater than 2, observed a 6, observed a 3. These are all mutually exclusive events. So if we see observed an odd number, and this is odd number, it is a mutually exclusive, because odd number, it may be 1, 3, 5 in the case of die. So 1, 3, 5 are the odd number. So it may means actually, if I looking for, it may come 1, may come, or 2, 1, 3, or 5. And like observed a number greater than 2, it means it may be 3 to 6, any number may arise. So these are not mutually exclusive. But if I see in the next two, observed a 6 means either we can get 6 or not. So it is a mutually exclusive, and observed a 3, these are mutually exclusive. Now if I take B and C together, so now we can see it is a mutually exclusive or not. If I see this is B is observed a number greater than 2, So if I see A and B together, so in A or B, so A is actually 1, 2, 3, and B is observed the number greater than 2. So if I take these two events, so if we can see that there is a 3 is common to both the cases A and B, so it is not mutually exclusive. But in C and D, you can see that it is a observed 6 C, and D is observed 3, so it is a mutually exclusive, means either 3 will appear or 6 will appear. I'm not talking about the exhaustive. It may not be, both may not occur also. So in the case of B and C, if I see B and C together, so B is actually observed a number greater than 2, and C is observed a 6. So it is a common, is 6 is common for both the cases B and C. So it is not mutually exclusive. But if I take B and D, since B and D observed a number greater than 2 and D is observed a 3, this is also not mutually exclusive, because 3 is common to B and D. So I'm going further, and that an event that cannot be, this is decomposed, it's called a simple event, and means we cannot divide into further. Like in the case of, say, if I say that, this is, we cannot divide into sub events. So in that case, it will called a simple events, denoted by E for we usually write an event. So each sample event, each simple event will be assigned a probability measure, how often it occurs, and this is the set of all simple events of an experiment is called a sample space. So now I'm formally defining what is probability of an event. The probability of an event A measures how often A will occur. We write PA, the probability of A. Suppose that an experiment is performed n times. The relative frequency for an this is relative frequency for an event A is so this is relative frequency of the event A is actually number of times A occurs divided by the number of time experiment performed. So F by N. F is the number of time A occurs and N is the number of time the experiment. So now if I take, if N is very large, this ratio will actually give you the probability of A. So if we let N gets infinitely large, then this actually then PA is actually the limit. PA, the probability of A is limit of this relative frequency. If I take the limit of the relative frequency, if N is very large, then this becomes the probability of the event A. So the probability of an event, it may be, so it will lies between, must be between 0 and 1, and 0 if the A can never happen. So then probability will be probability of A is 0, and if A is certainly happen, means always it will happen, A always occurs, then the experiment is performed, A is always happen, then the probability will be 1, and otherwise it will be in between 0 and 1. The sum of the probabilities of all this is simple events in S is equal to 1. Say if I taking a simple events like tossing of coin, head and tail. So the probability of head plus probability of tail, if a single tossing, so probability of head plus probability of tail will be 1. Similarly, in the case of die, there are 6 faces. So if I take all the faces separate events, say appearing 1, appearing 2, appearing 3 to 6. So the every that appearing 1 to 6, all the faces are probability is 1 by 6, because if I take a fair die, so it is a chances that every side can equally this equal probability of 1 by adding the probabilities of all the this is simple events containing A. Say I'm writing that A is actually I'm looking for occurring greater than 2. In the tossing of die greater than 2. So in that case, we can take the probability of actually coming 3, 4, 5, 6. So and in the case of die, each having 1 by 6. So it will be 4 by 6. The probability of greater than 2 getting strictly greater than 2, that and the event and that for the die. So it will be 2 by 3. So probability can be found using estimates from the empirical study and common sense estimations based on equally likely events. In the case of tossing coin, we are from the common sense itself, because there are only two sides are there, so it will be half only. So examples that probability of it is half. Suppose that 10% of the US population has red here, then for a person selecting at random, and here is red is 0.1, because we know that 1/10 of the US population having red here. So this is the probability of if I take a random person, so it's here will be red, its chances is 0.1. So now using simple events, the probability of an event A is equal to the sum of the probabilities of the simple events containing in A. Say if the simple events is an experiments are equally likely, we can calculate the probability of A, the number of simple events in A divided by number of the simple events. Say in the case of throwing a die and appearing odd numbers. So odd numbers in die is actually 1, 3, 5. So there are 3, and total number of events in die throwing, it is 1 to 6. So 3 by 6. So it is half. So another example, you can see that when we are throwing 2 dice, so these are from the school level statistics, because I'm just reviewing quickly those concepts so that we can go further. Say we are throwing 2 dice and we are observing that this is dice add to 3 that faces of appearing, and the sum of these 2 faces are 3. So it may be in the sample event, it may be first die is 1 and second die is showing 2, and other way also that first die is showing 2 and second die is 1, then also the sum is 3. So and the total this is in the sample space, because since we are throwing 2 dice and now counting principle shows that total number of this is in the sample space having 36 options, because if each die having a 6 options, so 6 into 6, so from the counting principle there are 36 options, and out of 36 options 2 options are 1 2 and 2 1. So this is probability is 2 by 36. Similarly for other cases. So I'm just coming to the conditional probability. Now another thing in the probability which is very important, because we know that the basic Bayes' law and other are based on conditional probability. So we have to know about what is a conditional probability. That the probability that A occurs given that event B has occurred is called the conditional probability of A given B is defined as this. That probability of A, this is probability of A occurs given that event B is already occurred. So this is equal to probability of A intersection B divided by probability of B. If probability of B is non-zero. Means if probability of B is 0, it means that B never happened. So in that case, we can calculate the conditional probability. So it means that B should to happen, and then only we, if we are calculating that B is already occurred, now we are calculating that what is the chance that A will occur. So that is actually the conditional probability of A by B. So now defining independent events with respect to the conditional probability. So we can define that event. This is define independence the terms of the conditional probability in terms of conditional probability. Say 2 events A and B are independent if and only if the this is conditional probability of A that B already occurred is equal to the probability of A, or the probability of B occurs when A is already occurred is equal to probability of B, then we call that A and B are the independent event. Otherwise, they are dependent. Now I'm jump to another thing, that the law of total probability. Law of total, this is total probability. Say S1, S2, Sk are mutually exclusive and exhaustive. Okay, exhaustive events means that if I add on all these events, it will give the total sample space. Then it is actually called the exhaustive. And mutually exclusive means there are no common outcome in the events. So if it is S1, S2, S3, Sk are mutually exclusive and exhaustive events, that is one and only one must happen, then the probability of an event A can be written as, say A can be this is a event A having many this is mutually exclusive sub-events. So in that case, if I calculate the probability of A, in this way also we can calculate the probability of A is equal to probability of A intersection S1 plus probability of A intersection S2 plus so on up to probability of A intersection Sk. And this probability of A intersection S1 also we can calculate using our we discussed the conditional probability law, that we can also calculate by the probability of S1 into probability of conditional probability of A when S1 is already occurred, plus probability of S2 plus into probability of A when S2 is already occurred, and so on. So if I sum up, that also give you the probability of A. Now, this we can also understand. Say there are this is A is our event, and S1 this is A intersection S1 is this portion. Say A intersection Sk is this portion, means we are dividing the whole event into different part, and then we are taking the intersection, and then we are actually intersections, that all the sum of the all exhaustive this is events. So we are taking that mutually exclusive and exhaustive events, and we intersection with A, and then this is probability. If you calculate and sum up, that will give you the probability of this A. So this is pictorial representation. So just we discuss this. Now I'm coming to next very important rule in probability. It is called Bayes' rule. Say let S1, S2, S3, Sk are mutually exclusive and exhaustive event with prior probability is PS1, PS2, Psk. If an event A occurs, the posterior probability Si we can calculate by this formula. Say the A is already this is A occurred. So what is the chances that this is Si will? And so this is actually we can calculate by this formula. This formula is called the Bayes' rule, because all of we know. I'm just quickly refreshing. So then we'll jump to our probability distribution. So this is actually law. So I'm just this we can discuss with an example, then it will be more clear. So this is actually Bayes' law. So we are actually, you can see that numerator is probability of Si and to probability of the conditional probability of A on Si, and divided by the sum of all possible cases, means we are actually normalizing this probability using the probability. So we can just see this proof is also one-line proof. So I'm skipping the proof, but I'm just okay. What is the use of this? Say I'm looking for a this is, we know that 49%. Say I'm just taking an example. We know that 49% of the populations are female, and of the female patients, 8% are high risk of heart attack. And while 12% of the male patient are high risk, a single person is selected at random and found to be high risk. So what is the probability that he is a male. He is a male. So I can see that how we can use that Beer's law for calculating the probability that this high risk person is a male. So we know, so I'm just defining that F is actually high risk. And H, I'm just defining the letter capital H is high risk, and F is the female and M is male. So we have given this, we have already given that female probability of female is 0.49 because it is a 49% of the population is female. So probability of female is 0.49 and probability of male, so it will be the remaining, so it is a 0.51, and then this is also given that female and the conditional probability that female and high risk of heart attack, it is given 8%. So this is also given, say this is given 0.08, and male, a male, and he having that this is high risk for the heart attack is 12%. So these are given probabilities. So from this example, these probabilities are given to us. Now we'll calculate that a person is randomly selected, and this is and found he is a high risk of heart attack. Now, what is the chance that that person is a male? So we have to calculate this probability that high risk. What is the high risk? The high risk of heart attack and he's a male. So this will be probability of male into probability of this is male high risk divided by probability of male into probability of male high risk plus probability of female and female with high risk. So just I am substituting these values that in the left hand side, the known probability. So if I substitute this values, so substitute these values, so we can get the probability that a randomly person is found they say high risk of heart attack and he's a male, it is 0.61. So 0.61. So this is just an example that we use these concepts in our from the school level also, but I'm quickly that these concepts that how we can use effectively the Beer's law, rule or the law. So now I'm coming to our main emphasis for this today's lecture is probability distribution. So probability, this is our continuous and discrete distribution. So first we have to understand what is a random variable. So random variable it is a numeric outcome that results from an experiment. For each elements of an experiment sample space, the random variable can take an exactly one value. And discrete random variable and random variable that can take on only one takes on only a finite or countably infinite set of outcomes, then that random variable is called discrete random variable. Means it is actually countably infinite, means it is a one-to-one mapping with a natural number. That outcome is actually mapped with a one-to-one mapping with a natural number, or it may be finite, In the continuous random variable, that can take on any value along a continuum, means along in an interval. It may be from any interval, finite or infinite interval, because it is a continuum, means it is a continuous values. So random variable are denoted by usually we denote by the uppercase letter like X. So individual outcome of for random variable are denoted by lowercase x. Means if X is the random variable, then this is individual members of that random variable, we can write by small, because all the probability distribution will use this this is a small x as the individual outcome of the random variable. So better understanding, I can also graphically that a random variable x represents a numeric values associated with each outcome of a probability distribution. So say here outcome maybe 2, 4, 6, 8. So these are actually, if the outcome is only 2, 4, 6, 8, so it is an only discrete way. It is in between 2 to 4. There is no outcome is possible, or 4 to 6 or 6 to 8. There is a no other outcome is there. Then we'll call it as a discrete random variable. And in the case of continuous, it may be that outcome is actually outcome may this is in the interval. It is a continuous fashion. We can get the value at 2, 2.1, 2.3, 2. Or even in between 2 to 4. We can have like under root 5. Under root 5 is also this outcome of this continuous random variable, because under root 5 is in between 2 to 4. So, but in the case of discrete, it is only this is if it is either 2 or 4 or 6 or 8. So this is the discrete cases. So I'm just taking this is another example that decide if the random variable x is discrete or continuous. Say the distance your car travels on a this is tank of gas. Say we have filled the gas tank, and then, or the petrol tank, and then we have to see that how much distance that car travel, that full tank, that the distance your car travels is a continuous random variable, because it is measures that the that cannot be counted. All the measures are continuous random variable here. In the case of number of students in a statistics class, so the number of students is a discrete random variable because it can be counted. So now I'm coming to first thing that we have to know about the discrete probability distribution. What is discrete probability distribution? A discrete probability distribution lists each possible values of random variable can be assumed together and its probability. The probability distribution must satisfy the following condition, that if it is a discrete probability distribution, it must satisfy the following condition. That first thing, that the probability of each values of discrete random variable is lying between 0 and 1, and it is also 0 and 1 is also inclusive, and sum of all probabilities should be 1. Means if I sum up for all cases, means where small x is the small x is an outcome of a random it is an out of a random variable. So if I over the whole random this is variable, if I sum up, then this sum will be 1. So just I'm taking that construct a discrete probability distribution. How we construct a discrete probability distribution? The guidelines, just I'm first discussing guideline, then we'll discuss some particular type of discrete probability distribution. Let x be a discrete random variable with possible outcomes are x1, x2, xn. So here, here in the beginning, x is capital X because it is a random variable, capital X. Let capital X be the discrete random variable with the possible outcomes are the small x1, x2, xn. Then make a frequency distribution for the possible outcome. First, we'll see what is the frequency distribution for all possible outcomes, means x1, x2, xn. What is the frequency distribution? Then find the sum of the frequencies. Find the sum of the frequencies. Then find the probability of each possible outcome by dividing its frequency by the sum of the frequency. Means what is the probability of x1, x2, xn, how we can calculate. If we know the frequency of x1, x2, xn, and we know the sum of the frequency, just we divide each of this frequency by the sum of the frequency, so we can get the probability of x1, probability of x2, and probability of xn. And then check that each probability is lying between 0 and 1. It will be always happen because we are dividing by the sum of the frequency and sum of the frequency. So now you can see we are constructing a discrete probability distribution. For a simple example, the spinning below is actually divided into two sections. The probability of landing means there is a spinning wheel, and there are two numbers are displayed, that 1 and 2, and 1 is occupied 25% portion of the spinning wheel, and 2 is occupying the 75%. So the probability of getting, if I spin the number, so spin this and this arrow will stop at 1 or 2. So what is the chances that, so we are actually that spinning below, it divides into two sections. The probability of landing on 1 is 0.25 because it is occupies only 25% of that circle, and this is probability of landing on 2, it is 0.75 because it is occupy the 75% of this region, circular region. So let x be the number the spinners land on. So our random variable is actually we are setting that random, that number be the number the spinner lands on. The construct a probability distribution of the random variable x. Now I will construct the probability distribution of the random variable x. It is a very simple. X can take two values, either 1 or 2. So now we'll calculate the this is from, it is obvious that that x, our random variable x, can take 1 or 2. So 1 can land, it is actually landing probability is 0.25, and 2 is landing probability is 0.75. And this will actually give you the each probability is between 0 and 1, and sum of the probability is 1. So it is satisfies the condition that for the probability distribution. So now we can write the this is probability distribution. So our probability, so we can write the probability distribute this px, it is actually this way. So our probability distribution, this is a probability distribution of this random variable x, which can take 1 or 2. So now I'm making slightly different problem of that earlier problem. That spinning below is a spin 2 times. We are actually spinning 2 times that same spinner. The probability of landing 1 is 0.25, exactly same as because it is only 25% of the circular region it is occupying, and landing of 2 is 0.75. Now, since we have spinning 2 times, and here I'm taking the random variable x with the sum of 2 spins. Now construct a probability distribution for the random variable x. So if I see that our random variable is sum of 2 spins, so x can, first spin x can land on 1, and second spin x can again land on 1. So it will be sum is 2, and it is a, if it is a first spin, it is a landing at 2, and second it is 1, so 3, and so on. So here x can take 3 values, either it is a 2, 3, or 4. So 2, 3, 4. So X can take 3 values. So unlikely to our earlier example that X can take only 2 values, either 1 or 2, because here we are X is the random variable where we are taking the sum of two spins. So in that case, the random variable this is random variable can take 3 values, 3, 4, 2, 3, 4. So here I'm just making, so the possible sums are 2, 3, 4. So you can see that this is probability of sum of 2. It is actually now I'm using again the it is counting principle, because both the spinning is independent to each other. So first spin outcome probability will be multiplied with the second spin outcome probability, then only we can get the joint probability of that. So we are making that sum probability of sum of 2. So we can see that spin 1 on the spin A1 on the first spin, it is actually 0.25, and since it is in the second spin also we are getting 1, so again probability is 0.25. So if I multiply 0.25 into 0.25, so the probability of sum of 2 is 0.0625. Now we got one that is probability that it is our first for 2, the random variable when it takes 2, then its probability is 0.0625. Now we'll calculate for other 2 cases, that what is the probability for 3, that sum is 3, and what is the probability of sum is 4. So probability of 3 can arise in 2 ways. One is that first spin it is coming 1, and the first spin it is coming the 1, and the second spin coming 2. So the probability will be 0.25 for the first spin, and for the second spin probability is 0.75. And if I take multiplication of these 2, will give you 0.1875. Or it may happen in other way, that in the first spin it is coming 2 and the second spin coming 1. So it is again the probability that the sum 3 in this way is 0.1875. So both the cases may arise. So So from the counting principle, so the probability of sum of 3 will be the addition of these 2 probabilities. So if I add these 2, so we can get the probability. So this is, you can see the sum 3, the probability is 0.375. So now the last one, and now we have to check that what is the probability that we are getting 4, sum 4. So we have to make for sum 4 that and the both the spin it should appear 2, that it we can get 2 in the both the spin, means its probability already was that 0.75 into 0.75. So this is the that sum 4, the probability is 0.5625. So we are making this is, and now if I add this 3 probability, it is coming 1, and all these probability is 0 and 1. So this is a probability distribution. So I'm making that example so that you can understand that how we can get the probability distribution. So if I see this last example in the histogram, so this will be the probability distribution of 2 is 0.06, and probability of 3 that random variable take 3, then its probability is 0.375, and for 4 it is 0.5625. Now coming to the mean of discrete random variable, how we calculate the mean of a discrete random variable. Mean of discrete random variable, if I multiply each outcome of the random variable with its corresponding probability and sum up for all outcome, if I sum up for all outcome, means it is a summation of x px. Already know that px is the probability of that outcome of that random outcome of the random variable, the probability of x And so if I multiply x into px and sum up this is all possible outcome of that random variable, that will give you the mean of the random variable. For example, in the last example, say we know that probability of getting this if the random variable 2, if the random variable takes 2, its probability is 0.0625. So we are multiplying 2 into 0.0. So this value, and 3, it is 3 is probability that x the random variable takes the value 3. Its probability of this. So px into px is this, and 4 this. So if I add this 3, so we are getting 3.5. So the 3.5 is the mean for the 2 spin. So this 3.5 will be the mean of the 2 spin sum. 2 spin sum mean will be 3.5. Now I'm coming to another measure in the random variable. This is discrete random variable. It is called variance. Variance is actually, if we can see the formula that sigma square, this is equal to, we are actually taking the mean deviations, the square of the mean deviations from the random variable, when this is square, into px, means x minus mu square px, and if I summing up over all possible outcome of that random variable, that will give you the variance. So same example, if I calculate the variance, so if we just see this table, and if I calculate, so here the variance is coming out 0.376. So the variance of this last experiment is 0.376. Its mean is 3.5 and variance is 0.376. Now standard deviation is the square root of the variance. So just once we know the variance, so just we take the square root of that. So that will give you the standard. This is standard deviation. And in this experiment, standard deviation is approximately 0.613. Now, expected value of a discrete random variable is equal to the mean of the random variable. So, sometime in the case of in the probability distribution, instead of saying that mean of the distribution, we also sometimes call it as a expected value of the distribution. Expected value of that random variable is nothing but the mean of that probability distribution. So you can see here it is actually denoted by ex. X is the random variable. So this expected value of the random variable is actually equal to the our mean of the distribution. So say in an example, at a raffle, say 500 tickets are sold at $1, and for 2 prizes are there. That one is $100 and other is $50. And what is the expected value of your gain? So expected value of your gain. So first we have to make a probability distribution. Then we'll see. Okay, so you know that if you gain 100, if you actually gain 100 prize, and since you have purchased that ticket with $1, so your gain is $99. And if you gain for 50, for 50 price, it is a $49. And what is the probability distribution for the possible gain of or outcome? So we'll calculate the possible gain. So possible gain, what will be our possible gain? Either it will be $99 or it will be $49 or minus $1. Means I have purchased the ticket, but I have not got any prize. So our random variable can take 3 values. So 99 gain means our random variable here, it is the gain is our random variable. So gain will be either $99 or $49 or minus $1. Means I have purchased the ticket, but I have failed to get any prizes. So you can see, since there are 500 tickets and $99, only one person can get the $100 price. So it is actually probability of getting a gain of 99. It is 1 by 500, and similarly in 49 gain it is 1 by 500, 1 by 500, and minus $1 gain is actually rest of the 498 cases out of 500. So probability will be 498 divided by 500. Now I'm calculating the expected value, and expected value for this gain. So we have to multiply this x into px and sum up for all possible x. Means here there are 3 possible x. So if I sum up, so we'll get minus 0.70. Means that the expected value is negative. You can expect a loss of $0.70 for each ticket you buy. So I'm taking another quick example. Some of the up faces of 2 die tables. Here the table value gives values of y for all this is elements in S. So we know that we are sum of the faces. We know that if it is there are 2 dice, one is red color and another is green color. So red color, if the red color die coming 1 and the green is 1, then the sum is 2, and red is 1 and green is 2, then sum is 3, and so on. I'm just making a 36 the 6 by 6 matrices for red and green, and so their outcome will ranging from 2 to 12, because sum of the dice. So it will be that list will be that both the die is coming one face, showing the one face, and the highest will be both the die showing 6. So all these values are ranging from 2 to 12. So if I say a random variable, y is a random variable, so y random variable can take the value 2, 3, 4, 5 up to 12. So it's in this experiment, the random variable, if the sum of faces of 2 dice, so the random variable can take the value from 2 to 12. So 2 to 12, and if I calculate the probability of this each cases, say 2, it is 2 is only 2 is only 1 places that 2 is coming. You can see that 3 is coming in twice, 4 is coming thrice, 5 is coming 5 times, and 6 is coming 5 is coming 4 times, 6 is 5 times, and 7 is 6 times, and 8 again it will reduce to 5, 9, 4, 10, 3, 11, 2, and 12, 1. So since it is actually, we can calculate the probability of each of this outcome of this random variable. So 2, the probability of 2 is 1 by 36, 3 is 2 by 36, and so on. You can see at the 7, y can take value 7, then its probability is 6 by 37, and then again gradually decrease, and at 12, when y is taking 12, the value random variable takes 12 value, then its probability is 1 by 36. Now if I if I calculate, this is actually cumulative, the capital Fy, I'm showing that cumulative probability. So you can see here we are adding all the previous probabilities. So it is actually, you can see this is our cumulative probability, capital Fy. So Py, so here I'm actually defining 2 things, probability mass function and cumulative density function. So you can see the probability mass function is actually density function or the mass function. Seeing that py, how we calculate the py, number of ways two dice can sum to y divided by that number of ways two dice can result in. So that will give you the probability of py. And fy, that cumulative density function, fy is the sum of the probability. Say we are calculating fy, so it is means our probability we have to sum up to y. So this is from our outcome is it is 2 to 12. Say I'm looking for f4, so we have to add on the probability of 2, probability of 3, and probability of 4. So here it is 6 by 36. So it is actually sum up to y. Up to y means here you can see it is important that here actually you can see here this is y, this y, and this is y, up to y, the cumulative up to that stage. Okay, so rolling of dice, that we know that in this experiment this will be the distribution. You can see that distribution is very uniform. Means it is a distribution, say gradually it is increasing. At 7 it is 1 by 6, 1 by 6, 1 by 6, it is from 1 by 36 to 1 by 6, and then again it will decrease. So it is a symmetric, and at 7 it is the highest chances that we can get the 7, and other cases are gradually decreasing. So just I'm plotting that earlier probabilities. And if we see the cumulative frequency will be like this. It's like a step function. So we are adding the previous probability. So this will be, so it will from 0 to means it will start from the first value of the random variable, and at the highest random variable cumulative frequency will be 1. So now I'm defining another very crucial things in the case of discrete or continuous random variable, that is called moments of random variable. So nth moment about the origin of a random variable x is defined by ex to the power n, and it is defined by, it is like in the case of expectation ex, if you remember ex, it is a sum of x into fx. So if it is e of x to the power n, so this in the case of discrete case, that sum of x to the power n into fx. Fx is nothing but our probability of x, means that we discussed earlier. So here fx will the probability distribution. So it is, instead of writing px, I'm writing in term of fx. I'm general. So this is, and we have to sum up over all the possible values of the random variable. And in the case of continuous, we have to do, instead of summation, it will be an integration between minus infinity to infinity. So as you see that if n is equal to 1, then ex is called the first moment about the origin, and it is nothing but the expectation or the mean of the this is mean. And for n is equal to 2, this ex square is called the second moment of x, and so on. So next I'm defining another thing. It is called moment generating function, because moment generating function is very important in a probability distribution, because if once we know the moment generating function, then rest of the statistical terms like expectation, variance, we can calculate from the moment generating function. Moment generating function, the definition is very simple, that MT is a moment generating function. It is actually expectation of e to the power tx. E to the power tx means it is a in the case of discrete case, it is actually we have to multiply the this is multiply e to the power tx into fx, and in the case of continuous case, it will be integration. So, in the case if x is a random variable whose moment generating function is empty, and n be any natural number, if n be any natural, what is the nth derivative of empty at t is equal to 0? So if I see moment generating function, if I differentiate first time this is actually, you can see that derivative of empty is equal to e x e raised to the power tx, e raised to the power tx. And if I put t is equal to 0 here, so this becomes the expectation. So if a first derivative of the moment at t is equal to 0 is the expectation. And if I calculate the second derivative, we will got ex square, and so on. So we can see at t is equal to 0, the moment the nth derivative will give you e x to the power n, means actually from moment generating function we can get the moment of the random variable. If I put the t's derivative, if I differentiate the moment generating function with respect to t and put t is equal to 0, means now the order of the derivative will determine what will be the order of the moment. So let x be a probability density function. This is a probability density function like this, or it is a discrete probability density function, or a random variable can take the value 0, 1, 2 up to infinity, and otherwise it is 0. So in that case, if I calculate the moment generating function, we can get the moment generating function, means if I do the summation, the e raised to the power tx into fx. So here you can see that x can take 0 to infinity, the values, and now and this density, our probability density is this. So I'm just actually rearranging. So rearranging, and it now this summation becomes an GP series with infinite sum. So I can apply the GP series that infinite sum is a by 1 minus r. R is the common ratio and a is the first term of the GP series. So this formula can sum up this series, and we finally we got the moment generating function as this. For it is only valid if it is actually t is less than, because I'm just taking the log on both sides, so we can see this actually our moment generating function. Now, if I differentiate this, so we can get its that mean of the distribution in the first derivative of the moment generating function, put t is equal to 0 in the last case, and then if we looking for variance, then you have to calculate the second moment, and we know that variance is nothing but the second moment minus first moment whole square. So from there also we can calculate the variance of that distribution. So this is moment generating function. I'm quickly going to the particular type of discrete and continuous distribution. I know that in a limited time I cannot give everything in detail, so but I'm giving the glimpse that you can understand how the distributions are formed, and then we can also have some examples, very quick examples, to understand that how the particular distribution actually works. So first I start with a most simplest discrete distribution is the binomial distribution. All of you know the binomial experiment. A binomial experiment is a probability experiment that satisfies the following condition. The first condition, that experiments is repeated for the fixed number of trials, and where each trial is independent of other trials. Second thing, that there are only two possible outcomes of interest for each trial. That outcome can be classified as a success or as a failure. So there are only two possible outcomes, the success or failure. And the probability of success is the same for each trial. We'll choose that that probability of success remains same for each trial. The random variable x counts the number of successful trials. So random variable x will count that how many this is how many success we got. So
Yes, sir.
we can see if I put these symbols in the binomial distribution. So I'm just putting n is the number of times a trial is repeated, and small p is the probability of success in single trial, and q is the probability of failure in a single trial. And since there is only two possible outcomes, so q will be nothing but the complement of p, means q is equal to 1 minus p. And x is the random variable. X is the random variable. Our random variable for the binomial experiment, say we have done n trials. So this is the random variable represents the count of number of success in n trials. So success we can get no success, say 0 success, 1 success, 2 success, or each trial is a successful trial, so n success. So we can have no success to all success. So here x, this random variable, our random variable x can take this value 0, 1, 2, 3 up to n. So our binomial experiment, just an example, say decide whether the experiment is a binomial experiment or not. If it is, specify the value of n, p, and q. Quickly we do this and list down the possible values of the random variable x. If it is not a binomial experiment, explain why. So you randomly selected a card from a deck of cards, and note that if the card is a S, so you can put the card back and repeat this process 8 times. So our success is if the card is coming S. So this is a binomial experiment because each of the 8 selection represents an independent trial, because we are replacing the card. So every time they are in the pack of card having a 4S, because it is either it is a success or failure in trials, but every time it is a new the independent trial. So each of the 8 selection represents an independent trial because the card is replaced before the next one is drawn. So there are only 2 possible outcomes. Either the card is a S or not. So our this is random variable. This is here also the card is S or not. So now what is our n here? You can see that n, our number of trials is 8. So n is 8. And probability of success, we know that there are 4 S in a pack of 52. So the probability of getting S is 4 by 52 is 1 by 13. And what is the probability of failure? It will be 1 minus P, so it is 12 by 13. And what is the actually this is our random variable can takes the value 0, 1, 2 up to 8, because it may happen that all these 8 trials we are never got the S, or once we have got S 2 times, 3 times, or all the 8 trials we got the S. So it is our random variable can take value from 0 to 8. So I'm quickly coming to binomial distribution formula. So binomial distribution, the binomial experiment, the probability of exactly X success in n trials are given by this formula. So NCX is the combination, all possible combination that out of the n trials, X success is the X success. So we are actually calculating NCX, and since out of this n trial, p times we have got the success. So, and since these are independent, each trial is independent, so we have to multiply the probability. So getting x number of success, though it will be p raised to the power x, and rest are failure cases. So in the n trial, so q raised to the power n minus x. So this is actually probability distribution, or you can say that mass function, probability mass function for the binomial distribution for x success. So x success. So a bag contains 10 chips, and 3 chips are red, and 5 chips are white, and 2 of chips are blue. 3 chips are selected with replacement. Find the probability that you selected exactly 1 red chip. Means we are looking for, say, our success is actually our red, exactly 1 red chip. So the probability of selecting a red chip is 3 by 10, because there are 10 packets, and out of that 3 are red. And probability of failure is actually 0.7, because it 1 minus 0.3. And here we have done 3 trials, so n is 3. And then our experiment, our success is that so we have to calculate 1 success, means only 1 red chip packets actually appearing. So x is, you can see that we are looking for 1 success, exactly one success. So we can calculate the probability from this above formula. So this will be 3C1, means out of this 3 trial, any trials we have got red chip, and so 1 time we have got success and 2 times failure. So our probability of getting 1 red chip is 0.441. Okay, I'm excluding the examples. There are many examples are there. So I'm just coming to. So sometimes we also do the this is, say we are we can say this example, that we have calculated, say the following probabilities distribution. This is distribution represents the probability of the selecting 0, 1, 2, 3, 4 red chips when 4 chips are selected. Means so this is actually, it may be that 0 success, 1 success, means say in the case of say we have done 4 trials, and so to getting red chip, it may be the no success is 0.25 24, and say it may be the no success that out of these 4 trials, or it may be 1 success, 2 success, 3 success, 4 success, and these are the corresponding probabilities. So now find the probability that selecting no more than 3 red chips. So we are not more than 3 red chip, means it is actually in the 4 trials we are looking for that we should get at the most 3 red chip out of the 4 trials. So we have to take the no red, 1 red, 2 red, or 3 red, and find the probability that selecting at least 1 red chip. So it will be p greater than 1. So greater than 1. So it will be, if I can also write the 1 minus probability of 0. So from there also means we are calculating the complement of no success. Then we'll get the probability of at least 1 success. So this is the binomial distribution of the last example. Now I'm coming to very quickly the mean variance and standard deviation of the binomial distribution. Mean of the binomial distribution, mu is NP, means number of trials into probability of success, and variance is NPQ. We can also calculate from we can also calculate straight way, because since we know that how to the mean of the distribution, means we have to calculate EX, expected value, and the case of variance. So I'm just in the case of variance, how we calculate the variance. We know that mean is nothing but the EX, and variance is our second moment minus square of the first moment. Means actually we can also have I'm just, if you know the formula, still I can write the. So in the case of I'm just making this. Okay, so in the case of say, I'm just making that mu is nothing. Sorry, make that pointer to pen. So mu is nothing but our EX, and how we calculate EX? EX is actually, we have to sum up X into Fx. And what is Fx here? Fx is our that success. So this is NCX, P raised to the power X, and Q raised to the power N minus X. And so from there we can easily only few rearrangement we can get NP. And in the case of variance, variance, we know that this is actually nothing but E of X square, means second moment, minus EX square. So it is better in the case of we calculate separately this, but we can directly calculate M. This is MT, that moment generating function in one go. Then by differentiating the moment generating function and putting t is equal to 0, we can get the first moment, second moment, and from there we can easily establish this mean, variance, and the standard deviation of the distribution. So MT, we know that MT is nothing but e raised to the power tx, and NCX, p raised to the power x, and q raised to the power n minus x. So first we sum up this, and then we differentiate with respect to t. We can get all this mean, variance, standard deviation. So I'm skipping because from school level we know that mean of a binomial distribution is this. So I'm going further. So I'm skipping this. So I'm coming to continuous distribution. Then we'll again jump to we'll go for few more discrete distribution, because discrete distribution is not only the binomial distribution. There are many other distributions like Poisson distributions, and many other distributions are very important. We'll also discuss gamma distributions and other. And now in the binomial distribution also there are few more variations are there, a negative binomial, and then geometric series, geometric distribution. Those are also important. So before that, I quickly brush up some of the continuous distribution, then again we'll back to the discrete distribution, so that side by side we'll learn both the continuous and the discrete distribution together. So because I know that time limits are there, so I have to quickly go through those distribution. So in the continuous distribution, let a random variable x denotes the outcome when a point is selected at random from an interval a to b, because it is in continuous. So it is not that discrete values like in the binomial distribution. We have seen that it is a discrete value takes 0, 1, 2, 3, but here it may take value in the any points in that interval 0 to a to b. We want to find the probability of the event x less than x. Okay, one more thing, in continuous distribution, say I'm looking for probability in the continuous distribution. If I say the probability of say x is equal to any point, say C, this will be 0, because if we see in the case of continuous where C is any point in the interval, where C is any point, C is any point in the interval AB. So in the case of continuous distribution, if I looking for a probability at a particular point, because probability is nothing but in the case of continuous distribution, in the continuous distribution, say it is our A to B, A and B, our distribution is like this, our distribution is like this. So actually if I calculate and this, if it is a probability distribution, then the this is sum of the this area under this curve will be 1 if it is a probability distribution. So if we are calculating, say x is any point here, x is any point. So if I looking for the this is our probability that our random variable takes values this is up to x means this values, this interval values only takes the random variable can take these values. In that case, it is nothing but that our probability will be the area under this. This area will give you the this area will actually this will give you the when the random variable takes the value x up to small x. So you can see that here how we have calculated. So this is actually probability. We can calculate the length of AX, length of AX means it is our length of AX by the length of AB. So this is actually, I can, okay, next PPT it is shown. So our probability of the cumulative density function fx we can write in the form that x minus A divided by B minus A. So this is actually this is now if this is the cumulative density in the if our cumulative distribution function is like this, so what will be the density function? We know that cumulative density function and density function, what is the relation in the case of continuous case? If I differentiate the cumulative density function, so we will get the probability density function. So just we fx, the probability density function, it is the derivative of the cumulative density function, and if I differentiate this, we'll get this. Means you can see that probability density function between A to B is the uniform 1 by B minus A. Means what will be the length of the interval, means that will be uniform throughout. So here if I see the graphically you can see this is the probability that graph. You can see that I'm writing the uniform random variable between 2 to 3. So 2 to 3, you can see that 2 to 3 it is actually uniform. It is uniform and actually the density uniform, and rest are it is actually 0. Only A to B it is this and rest as 0. And the cumulative it is actually written slightly wrong. It should be okay. It is 1 only because it is a 2 to 3. So between 2 to 3 the density will be 1. So you can see at 2 the density, because 1 by B minus A, B is 3 and A is 2. So it will keep at 1 constantly the density between 2 to 3, and rest of the part above 3 and below 2 the density is 0. So this is our probability density function, and if I see the cumulative density function, it is actually increasing from 2 to, so because cumulative density function is formula this is the cumulative density function. If x is equal to A, then this is 0, and when x is equal to B, then it is 1. So in between it will be 0 to 1. So and it is an increasing function. If I differentiate, and we can see that it is an increasing function. It is an increasing function. So our cumulative density function graph will be like this. Now mean of this distribution, mean of the distribution, we know that mean is nothing but the expectation. So here you can see that expectation of this random variable x, we can calculate a to b and x, and we know that its density function fx is 1 by b minus a. So if I integrate this with respect to x between a to b, we get our mean. And in the case of variance, how we'll calculate the variance? So we calculate x square. So first we'll calculate the second moment, because variance is nothing but ex square minus ex whole square. So we'll calculate first the second moment, ex square. Ex square is nothing but a to b x square of fx. So so if I calculate, so this will be and fx is nothing but 1 by ba. So 1 by ba is b minus a is coming out. So a to b x square dx. So this is 1 by 3 times of b minus a and x cube. So this is actually b cube minus a cube. Sorry, b cube minus a cube. Sorry, a cube. So if I simplify, so this will be 1 by 3 b minus a into b minus a to b square plus ab plus a square. So this factor is cancelled. So this is 1/3 of b square plus ab plus a square. So now we can calculate variance. So variance sigma square will be, we can substitute these values. So this will be sigma square is ex square minus ex whole square. So I'm just substituting this value because we already know the value of this. So this is 1/3 of b square minus b square plus ab plus a square minus 1/4 of b plus a whole square. So if I simplify, so it will be 1 by 12b plus. So this will be actually the variance. So we can calculate the variance, and the square root of the variance will give you the this is standard deviation. So I'm coming to quickly one example that if x is a uniform distribution, you have understand that its probability density function will be 1 by that length of the interval. So if x is a uniform distribution on the interval 0 to 10, then what is the probability? That x plus 10 by x is greater than 17. So here we have to rearrange in such a way that we can apply that our earlier concept of this is uniform distribution. So here x is a uniform distribution between 0 to 10. The probability density function of x is actually probability density function because it is a interval 0 to 10. So this is our probability density function. Hence we can rewrite this. We are just making simplification. So you can see that I'm making factorization. So it is getting this. So it is actually 1 minus p probability of that x lying between 2 to 5, and it is nothing but this integration of fx because we know that how to calculate the probability probability in that means in the case of continuous distribution, say we are looking for continuous distribution P, say A and X is actually in B. So this actually in the we can calculate this is A to B fx dx. So I'm just applying this formula here, so we can get the probability of this. Probability of this is 7 by 10 because fx here it is a uniform distribution between 0 to 10.
Sir, how is it coming 1 by 10? Sir, how is it coming 1 by 10?
This 1 by 10?
Yes, sir.
This is because just before we discussed that what is a uniform distribution. This is our uniform distribution. Uniform distribution between A to B, uniform distribution, if it is a uniform probability function, then fx will be 1 by b minus a. So
Yeah, it will be 5 minus 2, it will be 3, right?
yeah.
So that there the interval was 2 to 5, right? So 5 minus 2, it will be 1 by 3, right?
Which no fx remains same. Fx is actually density function. This is actually this defined. This is defined. So just I'm making this. This is our sorry. This is 0 and this is our 10. Say this is our 0 to 10 and this is actually 1 by 10. The value between 0 to 10 is 1 by 10. Now we are looking for this is 2 and 2 5. Say I'm looking for 2 to 5. So 2 to 5. So 2 to 5. So this will be how much? 2 to 5, 2, 3 because the 2 to 5. So we have to take this length. 2 to 5. 2 to 5. So but probability density function is 1 by 10 throughout 0 to 10, and now we have we have to see this area.
Okay, sir. Okay, that is the integration area. Okay. I thought
I already told that this is the integration. I think and the beginning itself I told that it is the integration. So you can see here that density is the area under the curve.
Okay. Understood, sir. Understood. Please proceed.
Okay. So now I'm coming to another example quickly, then I will go to the other distributions like normal distribution. So for uniform distribution, a box to be constructed so that its height is 10 inch and its base is x inch by x inch. If x has a uniform distribution over the interval 2 to 8, so we know that if it is a uniform distribution between 2 to 8, its probability density function will be this. So now we have to calculate then what is the expected volume of the box, in the in cube inches. So what will be the volume? Actually height is fixed 10, only base may change x by x. So it is actually v is equal to that volume is height is 10 and area on the base is x square. So this is our volume formula. Now we have to calculate the expected, because we have to calculate the expected volume of the box in cube inches. So we are calculating the expected value of v. So expected value of the v is e 10x square. So e 10x square. So 10 is constant. So we can take out. So ex square. Ex square. What do you mean by ex square? It is a second moment. So so this is, and since it is actually x is defined only in the interval 0 to 2. So second moment will be 2 to 8. So this is 2 to 8 x square 1 by 6 dx. So if I calculate. So this is simple integration. So we get this is because everything is in inches. So it will be, because we are calculating volume. So it will be in cube inches. So it is 280 cube inches. Very simple example I'm taking so that you can understand that use of that. So now in the case of more interesting and fundamental distribution is a normal distribution. if because I know that time running out of time, but I'll stop after normal distribution, and rest of the distributions like in the discrete distribution, like I'll discuss negative binomial and other in the next lecture, because I know that 1.5 hours I cannot discuss everything together. So but I will stop after the normal distribution. So I'll take another further 10 minutes, because all of you know the normal distribution. Still we have since we have to brush up our knowledge to because our main target is to understand the multivariate distribution in the next class. So these are the fundamentals. So this is why the normal distribution, the main importance of the normal distribution lies on the central limit theorem, which says that the simple sample mean has a normal distribution if the sample size is large. And so a normal distribution, I'm just straight away I'm writing a random variable x is said to be a normal distribution if the probability density function is like this. And here you can see that here random variable can take value from -infinity to infinity. If we see in the uniform distribution, it is in the finite interval a to b, and here it is for the whole range. And so where this is mu, mu can take any value between -infinity to infinity, and sigma square, it is a positive value, so it is 0 to infinity, arbitrary parameter. And x has a normal distribution with the parameter mu and sigma square. And mu is the we'll see the mu will be the mean of the distribution, and sigma square is the variance of the distribution. And we write so if it is a normal distribution, this random variable is normal distribution, so we usually write like this, that x is normal distribution with mean mu and the variance sigma square. So if we see the graphically, how it looks like normal distribution, because if I plot that, so this is actually normal distribution graph. So if it is if the mean is 4, and standard deviation on the variance is 1, so in that case normal distribution curve will be like this. This is a sharp. If the variance is more, so in that case it will be wide, and the mean is 8. So this is the second graph. It is actually normal distribution with mean 8 and standard variance is 4.
Sir, in the first it should be 4,2, sir, if I am not wrong.
Which one?
In the first graph it should be n 4,2, because
no, it is correct, because a mean is 4, and so it is actually, you can see it will it is not giving the range, it is actually giving the variance. So you can have 4, then it will be 5 first sigma. If I add 5, then 6, then 7, 3 sigma is almost, you know that it is almost covering 99%, and so on. It is correct. This is correct. 1 is actually giving the variance. It is not the range that only. So it can go, if it is a variance is standard deviation is 1. If the standard deviation is 1 and mean is 4, then from 1 to 7 it will cover 99.4% of the area. So it will cover, so it is from 1. So if it is a 1 to 7, it will cover the 99% of the area, and rest 0.06% will be beyond 1 and beyond 7. So this graph is correct. Okay, now I'm saying that if it is a normal distribution, then expected value will be this, and variance with this, and the our moment generating function with this. Because here, since it is a continuous distribution, and how we calculate the mean, variance, and more, so it is better first we start with a moment generating function, and differentiating the moment generating function and putting t is equal to 0, we can get the expected value and the variance. So this is because all of we know the its result. So in that case, I'm not deriving. But if it is required that for a particular new distribution, that how to generate how to calculate the expected value and the variance. So in that case, we calculate the moment generating function first, and then we can calculate expected value and the variance. We can calculate here also, but since the time is running out, so I'm just giving. So next is standard normal. Standard normal. So in that normal distribution, if I change x, that we know that x is a normal distribution. So x is a normal distribution with say mu is the mean and sigma square is the variance. So now I'm putting another say random variable y, which is related to x by this relation, x minus mu divided by sigma. So if I substitute, if I change the random variable x to y in such a way that y is equal to x minus mu by sigma, sigma. So in that case, our y will be a normal distribution. Y will be a normal distribution, and its mean will be 0, and the standard deviation will be 1, or variance will be 1. So actually this distribution with this substitution, y is equal to x minus mu by sigma, we can do a normal standard normal distribution. And in that case, standard normal distribution will looks like this. Just you can see, on the previous. So if I apply this changes, so we can get the standard normal distribution. Standard normal distribution, it is actually easier to present. So it is our mean is 0 and standard deviation is 1. So almost 99.4% of the area is actually lying between -3 to +3. So in the case of, say, I'm just taking an example that it is a initial that a problem is given in the framework. Say a problem is given in the normal distribution. We can change that normal distribution into standard normal, and then we can use the values to get the probability of a random variable in any finite interval. So for an example, so you can see that if x is a normal distribution with mean 3 and variance is 16, then what is the value of this probability of this random variable between the value between 0 to 8? We have to calculate this. So we can rearrange in such a way that you can see that here we are making a rearrangement that in such a way that x minus 3 by 4, it means we are making into a normal standard normal distribution, standard normal, because x minus mean by sigma. So this becomes means I'm putting this is z. So this is our standard normal. So it is actually, this calculation is now become the probability of the z lying between 1/4 to 5/4. It means that we have to calculate the probability of z less than 1.25 minus the probability of less than 0.25. So from the standard normal table available in books, so most of the books, so we can calculate these values and area under this curve. So from that we can calculate the probability of this. So since that I know that it is a lunch time also for everyone, so I'll stop. I will go further more discrete probability distributions because of which are more interesting than our basic binomial or the normal distribution that we discuss in the continuous case normal distribution. But we'll see that more practical use of the distribution. Normal distribution has a wide applications, and the standard normal, always we make it a standard normal to easily we can calculate the probability in the finite range because standard normal distributions tables are available, so we can use that table. So, but we'll discuss more distributions in the single variate and the multivariate distribution in the next class, because and one more announce for all of you, because I have a another talk, invited talk in an international conference from 2:30 to 3:05. So next class I'll schedule for you from 3:10 or 3:15. We'll start at 3:15 and we'll continue up to 5 at least, because I have to cover at least the basic concepts which is required for your next classes. So today's class I am rescheduling. Instead of 2, I'll start at 3:10. Is it okay for you?
Yes, sir, it is okay, sir.
So,
can you please open the slide after that normal distribution?
okay. Yeah, this one.
Sir, sorry, can you see it in full screen mode?
Yeah.
Sir, yeah, on normal distribution.
Okay, normal distribution. Yeah.
Yeah, sir. Here I couldn't understand in the first graph you said that is n normal distribution 4,1, where 1 is the variance, and second slide in the second graph it is showing 8,4, where 4 is the variance. I could understand, sir, how do you interpret variance as 1 and 4?
Yeah. Variance.
How did you interpret the variance?
Okay. Just I'm giving you one example. You know, this is, say, it is our this is our mean position, say mean position, and this is our mu plus sigma, mu plus 2 sigma. So okay, 2 sigma, mu plus 3 sigma. 3 sigma, and similarly in the right hand side also I can write mu minus sigma and mu minus, so here say mu minus 3 sigma, and you know that this between minus 3 sigma and plus 3 sigma, almost a whole curve must lie between
99.7%, sir. 99.7% of the data.
Yeah, 99. So this is actually the so you can see if now I'm just replacing whatever the value is given here. So 8,4. So if it is 8, then this will be 10, this will be 12, and this is 14, and this will be 6, 4, 2. So you can see here graph will be almost between 2 to 14. You can see graph is between 2 to 14.
Yes, sir.
And the first graph, you have understand that we can just make 4, 3, 2. So you have understand this graph. Okay. In the next lecture, I will discuss more on this because I have another event. So I will quickly take my lunch, and 3:10 we'll meet for the next lecture.
Sir, another one of my earnest request is that, like, if you can share your slides to Ajay sir so that we can get it via mail, because your slides are very illustrative and we have really grasped everything, and you started from the basics. So
I definitely this slides is for you only. I'll share the slide, but in between in slide when I write, if I save even, but it will not shareable. So I can share you slides, but in between whatever I write, it may be automatically erased when I save those files.
So we can look at the YouTube videos and just make the notes that you have.
Yeah, actually, Ajay sir also actually give you the video of this lecture also for you. He will also share the videos.
Hello, sir.
Yeah.
Sir, I have downloaded the lecture also. I will share it with the students.
Okay. So, Ajay sir, so
yes,
you are
sir.
also doing video of this lecture?
Yes, sir. Yes, sir. I am saving the video.
Yeah. So in that case, they can get the video lecture also, and if they want that my slides, I can give you that this PPT also you can share with you.
So we definitely want your slides there. So
yeah.
We want your slides there. please share it with Ajay sir so that we can get it and revise every content what you studied, what you taught today.
Okay. Definitely, definitely.
And
So,
sir,
Ajay sir, I can stop now and I can.
sir. I would like to thank you for for such a nice lecture, and I will request participants that you please join at 3:15 again. And I will tell you that sir is the Bible of statistics. You can learn a lot from him. So we will meet again at 3:15.
Okay. Thank you, Ajay sir. So we'll meet at 3:15 again for the.
Sir, one thing I would like to say, the best part of you is that you started from the basics, and even a person who has no knowledge in statistics, if he or she follows it, he will be able to understand everything. So that is the
So this
best.
is why I want to give you that whatever the knowledge you have, I have brushing up your previous knowledge, and now I'm moving towards the things which are slightly different from your earlier knowledge. Okay. Thank you. All.
Thank you, sir. Thank you.
Thank you.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Till then, you can have a break. We will meet again at
Thank you, sir.
3:15.
Sir,
Ajay,
how
sir?
will be the attendance will be taken?
I am taking that. You please don't.
Okay.
Ajay sir, please get the slides from sir so that you can share it
I
us
will.
to.
I
Okay,
will.
sir?
I will.
Sir, because the YouTube videos it depends on the internet connection, but the slides if we get once, so it will use for future reference, sir.
Yes. And I will request you again that sir knows a lot of things about statistics. You please take 100% from him.
Sure, sir. Sure. So we are definitely going to take that, sir. Thank you, sir.
Thank you.